Okay, so in today's class, what we'll be talking about is something called the concept of, I'll introduce you first to the concept of um, integral transforms. Okay, so there's something called as an integral transform. So what is an integral transform? We can talk about an integral transform because here the key word is a transform, right? So that means we are interested in some kind of a transformation from one thing to another thing. So which are the two things? We can make a transformation between two functions. So let's say one function is f of t and the another function is g of x. Okay, so these are our two functions, and here you can see f is a function of a variable t and g is a variable or is a function of a variable x. So there are two variables. One variable is your x and another variable is, sorry, one variable is t and the other variable is x. And then we have two functions. One function is a function of the variable t and the other function it's a function of the variable x. And these two functions, okay, that is f and g, these two functions, they are related to each other. And how are they related to each other? They are related to each other through an integral equation. You can see here this is an integration equation. Okay, so here we have an integral, as you can see, which is equation number 1. This is an integration of this function f of t. Okay, so we are having an integration of f of t, and not just f of t. F of t is multiplied with some function. That function is we call it as k, and this k is known as the kernel. Okay, this function k, which I have mentioned over here, this function is known as the kernel of this transformation. So this kernel k, as you can see, it's a function of both x as well as t. So here remember we are having two functions. Once again we are having two functions. One is a function of t, another one is a function of x. So there are two independent variables. One is t, another one is x. Okay, so these two independent variables, okay, x and t, we bring them together in one function, and that function is, I call it as the kernel function, and we refer to it as k. So this kernel function, and then you can see one more thing in this integral. It's a definite integral because there is a lower limit and there is an upper limit. So there are three things that we need to keep in mind when we are talking about a transformation like this. The three things are the lower limit, the upper limit, and this function, this kernel function. Okay, so these are the three things. So a, b, and the kernel. These three things, they will be the same for all such pairs of functions. So remember here we are talking about a transformation, and if you remember from your study of the vector spaces, so over there also we talked about transformation. So what is a transformation? Transformation is anything that takes you from one vector to another vector. So similarly here instead of vector we are talking about functions. So if you're going from one function to another function, so we are having a transformation. That means we are having a pair, right? So this is the pair that we are talking about. Okay, so for all such pairs of functions f and g, okay, these a, b, and the kernel function, they will be the same. Is that clear, everyone? So any relation, okay, if I have two functions of two different variables, and if these two functions, they are related to each other by this integral equation, then that is called, then we say that one function is the integral transform of the other function. Is this clear? Is this clear, everyone? If such a relation as given in equation number 1 holds good, then g of x, this g of x here, because g of x we write on the left hand side, and f of t we write it inside the integral. So we say that g is the integral transform of f. Okay, so g is known as the integral transform of f. Clear, everybody? Understood? Any questions? Okay, so we can write this in a much more shortcut form, because you see a is known to us, b is known to us, and k is known to us. So why simply waste time writing this integral every time, right? So instead of doing that, what we do is we can write it in a shortcut way in this format. So we can just have some kind of a symbol. So here I'm using the symbol. Usually the symbol is a cursive letter, okay, cursive capital letter. So I'm using the cursive letter T, okay, so T for transform. So here we have this symbol T, and this symbol T you are applying on the argument of this one is the function f, whose transform I want to find out. And so you are applying this one on this function, and you can see here this t, how is it defined? It is defined in this way. So t, you can immediately see it's an integral operator, because what is an operator? Operator is anything which you perform something on the operand and you give some kind of a result. So when this t, when it operates on f of t, this operator, integral operator, when it operates on f of t, it is going to give me some result. So it is an operator. Okay, so here we have t, and here I'm just putting a box here. You can put anything inside this box, any function inside this box. Of course it has to be a function of t, okay, because sorry, it has to be a function of x, because oh sorry, my mistake, it has to be a function of t, right, because we are integrating with respect to t. So you put any function of t inside this box, then whatever you put inside this box, that same thing is going to come inside this box over here. And when it comes over here and then you evaluate this resulting integral, then that is going to give us the integral transform. Is this clear, everyone? Have you understood this? Right now it seems a little bit abstract, but when we go to Laplace transforms, you will see the use of this one. In fact, you have already done one such transform, and that is a Fourier transform. We've already done that. Okay. So now if we choose specific values of a, b and k, they will give us different types of integral transforms. Okay. So choosing a, b and k, in this particular equation we get one specific integral operator, and that is going to give us the different kinds of integral transforms. So now we can talk about the inverse transform also. What is the inverse transform? Inverse transform is basically this. You see here we are having a pair of functions. Which are the pair? The pair of functions is g and f. So this is our pair of function. So here what is happening is, if you know f, you can find out g like this, right? And to help find out, we have this transformation, that is the integral transform. But can we find out, if we know g, can we find out f? And to do that, we will need some kind of an inverse operation of this t, and that is called as an inverse transform. Okay, so the idea of the inverse is basically it is to undo the effect of the transform, the original transform. Okay, so we are interested in such transforms where there is an inverse, the inverse it exists. Okay, so we can see here, so we wrote here g of x is equal to the transformation, the integral transform of f of t, which means f of t is equal to the inverse integral transform of g of x. Okay, so in that case t inverse, that is known as the inverse transform of the original integral transform t. Understood, everyone? Is this clear? Any questions? Do you have any questions? Anybody? Is this clear? Can I proceed?
Yes, sir.
Yes, sir.
Okay. So now some important integral transforms. Okay. One important integral transform we have already studied in your BSc, and that is the Fourier transform, right? So suppose I have a function of t is a function of time. Okay, so here t is f is a function of time. So because I'm writing t here, and then this function of time, if I multiply with e to the power I omega t, and then I integrate from minus infinity till plus infinity, then whatever result we get, that is called as the Fourier transform. Okay, is this clear, everyone? So we refer to this as the symbol for the Fourier transform. Here t, the t that I had written here, over here I wrote this as t. This t was in general for any integral transform. Okay, that's just a general symbol that I used. But Fourier transform, just to be very specific that we are talking about Fourier transform, you use a cursive version of the letter f. Okay, so g omega is equal to f of the f, capital F, the Fourier transform of small f of t. Okay, so that's your Fourier transform. Okay, so now we can actually identify the the kernel function and the a and b and the kernel function. Okay, we can actually go ahead and do that. So let me just grab this part. Let me get go here. Oops. Okay, so this was the general formula for the integral transform. I'll just keep this aside here. Now let's try to figure out what will be the kernel A and B. Okay, so let's try to do that. Okay, so let me bring this down here. Okay, so this is the expression for the integral transform. Let me put this over here, and then here. So what do we have here? Here, what is the kernel function? The kernel function, it's a function of x and t, right? Both the variables. So here, what are the variables here? The variables are omega and t, right? So the kernel function, it's a function of omega as well as t. Okay, so what will this be equal to? If you compare this equation, okay, if you compare this equation with the general form of the integral transform, you will find that the kernel function is simply e to the power I omega t divided by root over twice pi. Okay, remember the variables here. Here in general I'm writing x and t, but here I'm writing omega and t. Okay, so this is the kernel function, and what is a here? A is the lower limit and b is the upper limit. Here a is minus infinity and b is plus infinity. Okay, so this is your very familiar Fourier transform, and this Fourier transform, as you can see, it is an example of an integral transform. Okay, is this clear, everyone? What about then? What we are going to study here is what is called as a Laplace transform. Again, we can identify the the kernel, the lower limit and the upper limit. So in this case also, in case of Laplace transforms, let me put this down over here. Okay, so here, can anyone tell me what is the kernel function? The kernel function, what are the variables in case of Laplace transform? Just compare this equation with this equation. Just compare that. Anyone? Which is the kernel function?
S and t.
Yeah, here the variables are s and t. So we are making a transformation with between function of t and function of s. Okay, so what will be the kernel function? What's the kernel function here?
E to the power minus ts.
Yes, e to the power minus ts or e to the power minus st. What is a and what is b? 0, right? A is 0 and b is infinity. All right, everyone? So similarly, we have another kind of transform that is called as the Hankel transform, okay, which is defined in this way. This is the Hankel transform. Here, the kernel function, it is a Bessel function, okay. So we can write down the Hankel function. By the way, the Laplace transform, it is written in this format, okay. It's written as the cursive letter L. So like that, we have the Hankel transform also. The Hankel transform, it is written as cursive H, okay, and then we have another transform which is called as a Mellin transform, which is written as a cursive letter M. So I'll leave it to you to write down the kernel A and B of the Hankel as well as the Mellin transform. Okay, so that's about the integral transform. Okay, so now the question is, why are we studying integral transforms, right? So already you know that integral transforms are useful because you have some idea of Fourier transforms. You have already gone through a course in your BSc where you learned about Fourier transforms.
Excuse me, sir.
Yeah, tell me.
Sir, is it F or T, sir, for Fourier transform?
Which one?
Sir, the capital one. So G omega is equal to,
Hmm.
is it F?
Yeah, small letter f of t.
N-
You're talking
no,
about this
sir,
one?
the other one. No, sir, the
This one?
equation below. Yes, sir.
Yeah, this is the letter f, the cursive letter f.
Okay, sir.
Usually that's the
Okay,
practice.
sir.
The same letter for Fourier transform we use the letter f, the capital letter F, but cursive format. Okay. For Laplace transform, the capital letter L, the cursive format. Okay, so it'll be a good time for you to refresh, jog your memory as to how to write cursive, which you had learned maybe in your class 1. Okay, just refresh your memory how to write cursive letters. Hankel transform, and then you have the Mellin transform, same way. Okay, so the generic integral transform, I just wrote it as t here because it's not a specific integral transform, it's just a general integral transform, so I just call it as t. Okay, that's why I wrote it like this. Okay, yeah, sometimes I can understand, sometimes it looks like j here, but it's t here. Okay, any other questions? Okay, so now coming to this, you already have seen the use of the Fourier transform. You have already used, so you know that integral transforms are useful, okay, to some extent, because you have already used Fourier transform. So now I'll try to answer that question. Okay, but why do we have these different kind of transforms? Why do we need to study Laplace transforms or Hankel transform or Mellin transform? Why do we really need to do that? So in other words, we are interested in knowing why do we need to have integral transforms. Okay, so to understand why we need to have integral transforms, I would like to put this forward in this way. Okay, so suppose I have an original problem. Okay, so this is my original problem. Okay, and this is the solution to the original problem. Okay, so I want to go from here to here. Okay, along this path I want to find out the solution. The original problem is given to me and I want to find out the solution of the original problem. Okay, so now usually what happens is the original problem. Okay, if you try to solve this, if you want to find out the solution to the original problem, the method, the process that you have to follow if you want to directly find out the solution to the original problem, so it is difficult. Okay, this process, this way, it is difficult. You'll see some examples. When I do some examples, it is difficult. Okay, finding directly the solution, but we can take an alternate route here. The route is, first you have the original problem, you use the integral transform, you apply the formula for the integral transform. Okay, and then by applying the integral transform, you are getting the same problem, the same original problem, but now instead of the original space, you are now in the transform space. Okay, now once you are in the transform space, then you try to find out the solution. Just like you have the solution to the problem in the original, you have the solution to the original problem here. So you try to find out what is the solution in the transform space. Okay, and this is relatively easier. It turns out, if your choice of the integral transform is right. Okay, so this turns out to be relatively easier. Okay, so you can get the solution in a transform space with much lesser effort. Okay, and then once you get the solution in the transform space, then because you see you have integral transform, how do you go back? You have to undo the process, right? The process of the transformation, you have to undo it. So what you do is you perform the inverse transform. Okay, so essentially what we are doing is we are going from the original problem, you do an integral transform and you go to the problem in the transform space, but here the integral transform, you're using the integral transform, and then use with through a much relatively easier method, you find out what is the solution in the transform space. Once you have found out the solution in the transform space, then you take the inverse transform, and that is going to give us the solution to the original problem. We will see that, a few examples of that we will see, that will help you to appreciate this. So this is the reason why we need integral transform. It is just to make our job easier. Okay, is this clear, everyone? Is this clear, everybody? So for an example that comes to my mind is, let's say Fourier transform. Let's say you would have probably used some applications, right? Some applications where you record your audio, you record your voice, and then your voice, you can add some weird effects, right? In some app you might be probably using, right? Some of you, are using. Some of you, means most of you who are on social media, you would have probably used it. You record your voice and you can give some, different kind of funny effects, right? Can you do that? Have you all done? Anyone? So are you aware of what I'm talking about? Yes?
Yes,
No?
sir.
So how does that happen? How are you able to make do that so fast? You are recording the voice and in real time. Okay, you're able to see those effects. That's because here over there integral transforms are being used. So what happens is the original problem, that's your voice. Let's say you want to increase the pitch of your voice. Okay, that's the solution that you want to find out. But if you want to just capture the voice and from at every instant of time, let's say you want to change the pitch, that is going to be very difficult. So instead of that, what you do is you take your voice sample and you perform a Fourier transform. That means you go to the Fourier space, and then in the Fourier transform it will give you, because voice is it's amplitude versus time, and then when you go to Fourier transform it will give you amplitude versus frequency. So it will directly tell you what are the frequencies that are available in the voice sample. Okay, so once you get the frequencies, then you can play around with those frequencies. Maybe you can reduce the lower frequencies, increase the higher frequencies. You can do all of that. So that is relatively easier. Once you are satisfied with the result, then that means you get the solution in the Fourier space where the pitch has increased. Now after you have got the transform Fourier the Fourier transform, then you do an inverse transform that is going to give you the same voice sample but with a higher pitch. Okay, so that's an example. So inside that application, what is happening behind the scenes, you all are just using the application and you feel share it with your friends and it goes viral, and then you feel happy about it. But what's happening inside, okay, is all integral transforms. Okay, so that's why these integral transforms are useful. Okay, that's just a silly example of how you can use integral transforms, but there are many other uses also. Okay, so the integral transform that we are interested in, that is called as the Laplace transform. So we have already seen how is the Laplace transform defined. It is defined in this way. The kernel function is e to the power minus st. The lower limit is 0 and the upper limit is infinity. And then we have some function f of t. And then when you evaluate this integral, whatever result you get, that will be a function of s. Okay, so that is said to be the Laplace transform of the original function. Okay. So what are the uses of the Laplace transform? First of all, one way is it can convert. It gives you a way to convert a function of a real variable. So f of t is a function of a real variable, and f of s is a function of a complex variable. So s could be a complex number. Okay, need not always be complex. Many cases it will be real, but in general this s could be a complex number. So you can convert from, you can transform a function of a real variable to a function of a complex variable. That's the first use. Usually these variables that we are talking about here, t and s, okay, so these are the pairs of variables. So t is usually considered to be, this is a real variable, it is usually taken as time, and s is usually taken as the complex frequency. Now again, what is complex frequency? The concept of complex frequency, right now it may seem a little bit weird, but next semester when you do electrodynamics, over there we will be studying about the complex refractive index, and there you will be introduced to the idea. When we study electromagnetic waves, you will get to know about the complex frequency. Okay, so such kind of transforms you can easily do using Laplace transforms. So this Laplace transform is basically a very important tool for solving differential equations. We will do that in one of our applications will be solving a differential equation, and you can see the amount of effort. Okay, let's say the harmonic oscillator problem, you solve it normally, you know how much effort you have to put in, but if you use Laplace transform, you can easily see that it reduces the amount of effort that you need to put in. Okay, so lots of applications in science and engineering, over there the Laplace transform is used, because engineering especially, you'll know, if you have some friends in engineering, you can ask them, they have a lot of problems and those problems involve differential equations. Okay, so solving these problems of differential equations in engineering, the Laplace transform, it gives you a very easy way to do that. Okay, why the Laplace transforms are very popular? It is because they convert a linear differential equation. Okay, you can see that a linear differential equation, becomes an algebraic equation. An algebraic equation, you already know, it is very easy. It's much easier to solve an algebraic equation than a linear differential equation, right? You'll agree, right? So Laplace transforms, this is the power of Laplace transform. They can convert linear differential equations. Okay, a linear differential equation can be converted into an algebraic equation using Laplace transforms. Okay, is this clear, everybody? Is this understood?
Yes, sir.
Okay, then there is another operation called as the convolution operation. We'll do that. Okay, there's something called as a Laplace convolution theorem. When we do that, I'll explain what convolution is. It is basically you are taking an overlap of a function with another function with time. Okay, so convolution function, the convolution operation, it simply turns into a multiplication operation. Okay, so convolution is not easy. It's mathematically it's very challenging. It's a very challenging operation. But using Laplace transform, you can easily convert a convolution operation into a simple multiplication operation. Okay, so these are some of the uses of the Laplace transforms. Okay, now before we proceed with the Laplace transform, first a basic question: how do you know whether Laplace transforms exist or not? Okay, so what are the conditions for the existence of Laplace transforms? Is I think there is some lag in the video that you're getting. Let me just stop my presentation and continue again. Just a minute. Let me know if you can see my screen. Is my screen visible
Yes,
now?
sir.
Okay. So the existence of Laplace transforms. Okay.
Yes.
Yeah. So for the existence of Laplace transforms, there are certain parameters. One parameter is your S naught. Okay. Another parameter is a quantity called as M. So S naught is one parameter, and M is another parameter, and one more parameter is T naught. Okay. So as you can see here, S naught, M, and T, they are all related to these variables. Okay. So this T naught that we're talking about, the function f of t, capital F of t, that function f of t, it's a function of time, and this time the time must be greater than this t naught. Okay, so for all t which is greater than t naught, then this the upper limit of this function, that is e to the power minus s naught t f of t, the upper limit of that, it must be less than or equal to m. Okay, this result that we get over here, this result that I have written over here, you can take a guess as to where this result comes from. This result, it comes from the ML inequality, which you are already familiar, because like I said, the Laplace transform, it transforms to a function of complex variable. Okay, so we can get this from the ML inequality, but I'll not really go into that one. Okay, so if that is the case, if this condition holds good, then the Laplace transform of this function, okay, the Laplace transform of this function, it will exist, and then this function f of t, it is said to be of exponential order. Okay, so we say that the function f of t, just a minute, we say that this function f of t, we say it is of the exponential order. Okay, so when this condition is satisfied and the Laplace transform exists, then it is said to be an exponential order. So this diagram is important because it tells you what is the over which you have the Laplace transform is defined, over which range. So there is some time t naught. Okay, there is some time t naught, and for all t which is greater than this time t naught, which I have circled over here, for all t greater than, for this one, for all t which is greater than t naught, okay, for all t greater than t naught, the function f of the original function f of t, it is defined within this region. Okay, the original function f of t, it is defined within this region. Then correspondingly we have a value s naught. Okay, a value s naught is there, and this S naught, for all S which is greater than S naught, the Laplace transform for all values of S greater than S naught, the Laplace transform will exist within this region. Okay, so we are only interested in those t which is greater than t naught and those S which is greater than S naught. Lesser than t naught, that is on this side. Okay, lesser than t naught, that is this side, and lesser than S naught, which is this side. These two regions, they are not of any consequence to us. Okay, this is one condition under which the Laplace transform will be it will exist. Okay, so there's another condition, and that is if the function, the original function f of t, if the original function f of t itself has got a singularity at t equals t naught. Okay, if the original function, that's given in point number 2, if the original function itself has a singularity at t equals t naught, then the Laplace transform, it does not exist at t equals t naught. So these are the two conditions under which the Laplace transform will not exist. Okay, now another property of the Laplace transform, which is called as the linearity property, a very important property because that is going to help you solve a lot of problems. What it says is, suppose I have two functions f of t, okay, one function f of t and another function g of t. So there are two functions f of t and g of t, and we are assuming that for these two functions, for both of these functions, the Laplace transform, it exists for both of them. Okay, the Laplace transform, these functions, they exist. Then we have the Laplace transform of a linear combination. That's why it's called as a linearity property, because we are talking about a linear combination of these two functions. So the linear combination of the Laplace transform of a linear combination of functions is equal to the linear combination of Laplace transforms. So I could maybe write this down over here. That is the Laplace transform of a linear combination of functions equals the linear combination of their Laplace transforms. Okay, so in other words, it really does not matter whether you first take the Laplace transform, okay, and then take the linear transformation, or first you take the whether it doesn't matter whether you first take the Laplace transform and then you take the linear combination, or first you take the linear combination and then you take the Laplace transform. It really does not matter. The result is going to be same in both the cases. So that is the linearity of Laplace transforms. Okay. So now let us find out the Laplace transform of some elementary functions. So we'll start with the simplest function, that is called as it's basically a step function. So we have a scenario where at t equals 0, okay, and for t less than 0, okay, for this part, for t less than 0, the function f of t, it is having the value 0. Okay, for t less than 0, the function is having the value 0, and for t greater than 0, it is having the value 1. Okay, so let us have a function like this. So I want to find out the Laplace transform of such a function. Okay, so the Laplace transform of such a function, that is in other words, we are trying to find out the Laplace transform of this 1, because that's the value, that's 1 here. So we are trying to find out the Laplace transform of this constant function for positive values of t. So what will that be equal to? Just apply the formula. The Laplace transform, as you remember, it is whatever is the function times e to the power minus st, and you integrate that from a to b. So here a, okay, is 0 and b is infinity in case of Laplace transform. So integrating from 0 all the way till infinity. So 1 e to the power minus st, and as a result we have, because it's 1 so it won't make any difference, so we'll simply have integration of e to the power minus st dt. So now this integration of this one we already know, it is minus e to the power minus st by s. So this is the result of this integration. Okay, so once you know the result of this integration, then you have to just put the lower limit and the upper limit. What we will do here is, because we have a minus sign over here, so because of this minus sign I could get rid of this minus sign by swapping these limits. Okay, the upper limit and the lower limit, we can just swap them, and that is going to absorb the minus sign. So that's what I have done here, put the 0 up above and infinity below, and this gets rid of the minus sign, so 1 by s. So I can take 1 by s common, and then upper limit is 0, so we have 1 by e to the power 0 minus 1 by e to the power infinity. This is going to give us 1 by infinity, which will be 0, and 1 by e to the power 0 is 1 by 1, so we'll get 1 here. So as a result we'll get the Laplace transform of 1 is equal to 1 by s. And for this, the condition, the s naught value, remember here, so we were talking about for the existence, there is some constant s naught. So the s naught is such that the Laplace transform, okay, it is always ensured to be positive. Okay, so we have here, the only way to do that will be the denominator. Of course it should not become infinity also. The denominator, if you make it greater than 0, so s is greater than 0, so that is going to give us the Laplace transform. So this is how it transforms. So this was the original function. The original function was a step function like this. The Laplace transform function is something like this. Okay, is this clear, everyone? Have you all understood? Is this clear?
Yes, sir.
Okay,
Yes,
so
sir.
I'll leave this to you as a homework. Okay, this one, this is homework for you. Okay, okay, please do this at home. This is just you have to use this result from the previous one. You have to use this result and the linearity property. Using that, you can show that the Laplace transform of some constant a is equal to a by s. Okay, so that's one example. Another example is that another elementary function is, let's say the function f of t is equal to e to the power kt. K is some constant. It could be positive, it could be negative, but t is always positive. Okay, let's say we have this scenario. I want to find out what is the Laplace transform of this function e to the power kt. So how do we do that? So we go ahead and we want to find out f of s. So f of s is nothing but the Laplace transform of e to the power kt. So apply this formula. So we have e to the power st, that is minus st, that's the kernel function, lower limit, upper limit, and then we have this function which we are trying to find the transform of, that is e to the power kt. So we can combine these two together, because if we combine it, because that is exponential function and there is t here, so when we combine them, I could write this as minus s minus k times t, e to the power minus s minus k times t. And this one, if you integrate this, you will get this to be 1 by s minus k e to the power minus s minus k into t. Okay, so this is what you will get if you integrate this. And of course there will be a minus sign, same reason as before, that minus sign will be there provided we have lower limit. Here we have 0 and upper limit we have infinity, but you can notice here I have swapped the limits. So we have 0 to infinity, I have swapped it. That means I have absorbed that minus sign inside, so that's why we don't have a minus sign here. And then I can take 1 by s minus k, I can take it common here, substitute t equal to 0 and t equal to infinity. So this is what we get. So that gives us e to the power kt equal to 1 by s minus k, where, and of course the condition is the denominator must be non-negative. Okay, it must be positive, so s minus k must be greater than 0, which gives us s is greater than k. That gives us a condition pretty much in the same way as we got over here. So here we had s, here we had 1 by s, the denominator was s, so we have to make sure that the denominator is greater than 0, so we have s greater than 0. Okay, everyone? So same thing over here also. So denominator is s minus k and denominator is s minus k, so which means we have to ensure that s minus k is greater than 0, which gives s is greater than k. Okay, so now for two cases, one case is k is greater than 0 and k is less than 0. If k is greater than 0, then the exponential function, this is what it's going to look like, e to the power kt. This is how the exponential function will look like if k is greater than 0, and if k is less than 0, then this is how the exponential function will look like. then the Laplace transform, the only difference in these two cases, you can see here, both of the functions, they are totally different. In the original space, both of these functions, they are totally different. But in the Laplace transform space, you see, this is the only difference between them is k is positive here and here k is negative. Otherwise, the functions look exactly the same. Okay? Is this clear, everyone? Understood?
Yes, sir.
Yes, sir.
Okay, so now next function that we'd like to find out is the Laplace transform of the hyperbolic cos function, hyperbolic cos h kt. Okay, if you remember your undergraduate course again, the hyperbolic function is defined this way: cos hyperbolic kt is equal to half e to the power kt plus e to the power minus kt. In case of sine hyperbolic, there will be a minus sign here. Okay, so for cos it will be e to the power kt plus e to the power minus kt. So now I want to find out the Laplace transform of this. So the Laplace transform of hyperbolic cos is equal to the Laplace transform of this. Okay, so which is the Laplace transform of this. Now which rule had I used? I have used the property of linearity, because this is some constant into some function plus some constant into some other function, and that constant has to be happens to be same, so I am taking it common. So that's basically the linearity property. So this constant I bring it outside, and then I apply the Laplace transform on the individual functions. So Laplace transform of e to the power kt and Laplace transform of e to the power minus kt. This is already done. Laplace transform of e to the power kt we have already done over here. Laplace transform e to the power kt is 1 by s minus k. We have already obtained that. So this is going to give us the Laplace transform of e to the power kt. Okay, so this is going to give us this 1 by s minus k, and the Laplace transform of this other one, okay, that also we can obtain it from here itself. Wherever there is k, you can see here the only difference is this k, and here there is minus k. So just replace k with minus k and you get this. So earlier it was s minus k, so put k becomes, replace k with minus k, we get s plus k, and that's why we get s plus k. Okay, so now combine these two together. So we have s minus k, s plus k, it gives us s square minus k square, and then this s plus k comes over here, so s plus k plus s minus k, and then what will happen is this plus k and minus k, they will get cancelled out, and once they get cancelled out, so we get what is left behind is twice s, 2 and 2 will get cancelled out, and as a result this will be the Laplace transform of the hyperbolic cos, s by s square minus k square. Okay, here also the denominator has to be positive, so it means s square minus k square must be greater than 0, which means the only requirement is s is greater than k. Okay, if that holds good, then it is guaranteed that the denominator will always be positive. Is that clear, everyone?
Yes, sir.
Okay, so I leave this to you as homework. You can see here it's pretty straightforward, right? Very simple. Okay, the problems are not at all difficult. Very simple, very simple. So this problem I'll leave it to you as a homework. Okay, so please do it in the same way as we had done for the hyperbolic sine kt. Then cos kt, this is different. Okay, so this was hyperbolic cos, this was hyperbolic cosine, and then here next we have the trigonometric cosine. Okay, so these are two different functions. So I want to find out the Laplace transform of cos kt. So we already know, we have already found out the Laplace transform of the hyperbolic cosine function. We have already done that here. But we know that there is a relationship between the hyperbolic cosine and the trigonometric cosine. Okay, so the trigonometric cosine is nothing but the hyperbolic cosine of I kt. So if I put a theta here, the actual relation is this. The actual relation is cos theta is equal to hyperbolic cos I theta. Okay, so this is the actual relation. Okay, so we just, instead of theta we put kt. Okay, that's what I have done over here. So we use this relation here. So it means I want to find out the Laplace transform of cos kt, that is equal to Laplace transform of cos I kt. Okay, so hyperbolic cosine, we already have the formula here. The hyperbolic cosine is s by s square minus k square. So wherever there is k over here, this k I replace it with ik. Okay, the hyperbolic cosine k replace with ik, We had here earlier s square minus k square, s square minus k square here. So if I replace k with minus k, we'll get minus I square k square. I square will give us another minus, that minus and minus will give us a plus sign here. So we'll get s square plus k square. So hyperbolic cosine, this is the Laplace transform. Okay, once again here the relation must be s must be positive. It is enough. Here unlike this one over here, s had to be greater than k, right? Here in the hyperbolic case, s had to be greater than k. That's the only way we can ensure that the denominator is positive. But here no such rule. Okay, the only requirement is s is positive. If s is positive, that's more than enough. Okay, is this clear everyone? Because there is a plus sign here, that's why. Okay, understood everybody? So in a similar way, I would like you to do this also as a homework. Work out the Laplace transform of the sine function. Okay. So it turns out to be this one. Okay, you just have to prove that. All right. Next example is let's say I have this function t to the power n. Okay, the t to the power n, the polynomial function, where n is greater than minus 1. So n could take the value 0, 1, 2, 3 and so on. Okay. So for that, we'll recall the gamma function. Okay. Remember the gamma function from your undergraduate, or maybe when we discuss Bessel functions, over there also I talked about the gamma function. So this is your gamma function. Okay, so gamma is defined as gamma of n is equal to integration from 0 to infinity u to some variable u to the power n minus 1 e to the power minus u du. Okay, and then what is gamma of n plus 1? To find out gamma of n plus 1, all you need to do is in here just replace n with n plus 1. So you replace here, you put n plus 1. So the only place where we have n is over here. So this gets replaced with n plus 1. So n plus 1, then there is a minus 1 here. So n plus 1 minus 1 is going to give us u to the power n. So this is what it is. So gamma of n plus 1 will be equal to integration u to the power n e to the power minus u du. Okay, so now over here I would like to find out the Laplace transform. We'll just keep this result aside. Now I would like to find out the Laplace transform of t to the power n. So just apply the formula. So Laplace transform is whatever is the function t to the power n e to the power minus st dt. Now I'll make a substitution here. The substitution is let us say u is equal to st. I define a new variable u, and that u is equal to st. Basically this function, this quantity that I have here, e to the power minus st, that one I just write it as u. Okay, then if u is equal to st, that means t is equal to u by s. Okay, so if I differentiate, du is equal to s dt, which means dt, okay, dt is equal to du by s. So now going back to this function and this expression, so the Laplace transform of t to the power n is, so here t I replace with u by s. Okay, so we have u by s whole to the power n because there was t to the power n, e to the power of, here st is there, st is nothing but u. Okay, so e to the power minus u. Okay, and then we have dt, dt is nothing but du by s. So we make the substitution. Then you can see here we have in the denominator we have s to the power of n, because there is a power of n here, and then we have s. So in the denominator we'll have s to the power n plus 1. So that I can take outside the integral, because here we are doing integration with respect to u. Okay, so because we are doing integration with respect to u, so I can take s outside, because u varies with t, because I'm just differentiating. I'm assuming that u changes with t. Here I'm assuming that s is a constant. So because s is constant, it comes outside the integral. And then we have u to the power n, integration from 0 to infinity, u to the power n e to the power minus u du. And then we realize that this integral that we've got, it is the same integral, right? So which means this is nothing but the gamma function. So I could just go ahead and replace this integral, I could just replace with the gamma function, which is gamma n plus 1. And the moment I do that, so this gives us the this Laplace transform of t to the power n is gamma n plus 1 divided by s to the power n plus 1. So over here the requirement is s is greater than 0. Okay, so the only requirement is s is positive, and then n is greater than minus 1. That of course is from the original problem itself. Okay, so these are the Laplace transforms of some elementary functions. Okay, is this clear everyone? Understood? Okay, Okay, so now we go to table of Laplace transform. So this summarizes the results that we got. So for instance, okay, some more results are given. The Laplace transform of the Dirac delta function, which is 1. Then this is what we started with. We did this, right? We found out Laplace transform of 1, which is equal to 1 by s. Then Laplace transform of t to the power n is gamma n plus 1 by s to the power n plus 1. I just picked up this table from Arfken. The Laplace transform of e to the power kt is 1 by s minus k, and so on. Okay, so you can get this relationship between the different Laplace, the function and its Laplace transform. You can get it from this table. Okay, so this is the function and this is the Laplace transform. Okay, so this is equal to the Laplace transform of this. The function in this column, the function in this column is the Laplace transform of the function in this column. Okay. So much of these functions we don't really derive in this way, the way we have derived for these functions. We generally don't derive it this way. So we just derive it for the first few functions, and then using certain properties of the Laplace transforms, we can actually build this table by ourselves. Okay, so I'll go to that a little bit later on. So before doing that, let me just tell you about the inverse Laplace transform. So you see, an integral transform, okay, it is useful only if you can carry out the inverse transform. Okay, because of this reason. If you can't carry out the inverse, if you can't carry out the inverse transformation, it's of no use, because this is the whole purpose. I have the original problem, and then I want to find out the solution to the original problem. To find out the solution, what we do is we do a Laplace transform. Okay, you do a transform from the of the original problem. You transform it to the takes it to a transform space, and then from here you find out the solution in the transform space. But if you don't know the inverse transform, then you will be stuck over here. You will not be able to come back to the original domain, right? Is this understood? Is this clear? Have you understood this? Shall I repeat?
Yes, sir.
Yes, sir.
Okay. So the point that I'm trying to make here is just knowing the integral transform is not enough. You should also know the the inverse transform. Okay. Otherwise, from the original problem, you go to the transform space. Okay. So we have the original problem here. You go to the transform problem in the transform space, and then you find out the solution. Once you found out the solution, then you're just stuck over here. You cannot come back. Okay. You're not able to come back to the original space. Okay, so you will be like, in Mahabharata there is the story of Abhimanyu, so it will become like that. You will be able to enter the formation, but you can't come out of the formation. That's what happened to Abhimanyu, and he died, right? So we need to have some idea about the inverse transform. So a transform is of no use until and unless we know its inverse. Okay, so suppose I have a Laplace transform, a function, okay, f of t, and this function's Laplace transform is f of s. So f of s, we write it as is L of f of t. Then the inverse transform is, if you know here, what it means is, if I know f of t, I can find out f of s. The inverse transform means if you know f of s, okay, if you know f of s, that is this one, then you can find out f of t. And to do that, we have this inverse transform. Okay, so the inverse transform is of really is of great importance to us. Okay, so but one thing about Laplace transform, one thing you have to be cautioned about is in case of Laplace transform, the inverse is not unique. So it is possible that you get you get a result, and then you try to take an inverse. You may end up with a function which is totally different from your original function. That's because the inverse Laplace transform need not always be unique. Okay, so when we'll have two different functions, when will they have the same Laplace transform? Two functions f1 and f2 will have the same Laplace transform, provided their difference, the difference between the two functions. That is, if I take f1 minus f2, and that difference function I call it as n, and this difference function, if I integrate from 0 to some t0 is greater than 0. So if I integrate this from 0 to t0, and if this integral happens to be 0, then we know that this f1 and f2, both of them will have the same Laplace transform. Okay, so this is how we can actually figure out whether the inverse transform, whether it is unique or not. Okay, by the way, there is a name which is given to this, what I have stated over here. There's a theorem for this. It is called as the Lurch theorem. So this Lurch theorem is used for finding out whether a given Laplace transform whether it's unique or not. Okay. Now, how do you evaluate the inverse Laplace transform? There are mainly three ways to evaluate the inverse Laplace transform. Firstly, you can use a table of transforms as we did over here. Okay, so just like how over here we had this table of transforms. So you can use a table of transforms. So in the table of transforms, all you have to do is, look at the function and then tell what is the transform. Or let's say you get a function like this. What is the inverse transform? We look at the table and we know that the inverse transform is this. So just looking up at the table, we can find out what is the inverse of that particular Laplace transform. So this is the first method. So a table of transforms you can build up and then you can use it to identify inverse transformation. So this is very similar to, in your lower classes you did the log and the anti-log tables. So it's very similar to that. Okay, so using a table of transforms. Another way by which you can find out the inverse transform is by using the inverse transform by using the calculus of residue functions, which you have learned. And the third way is by numerically finding, you can find out the inverse numerically. There are lots of algorithms which are available, Krylov, Sklobiar, these are two names of two algorithms. So you can calculate the inverse Laplace transform using these different algorithms. But what we will be doing here, the most convenient and the most, the easiest way, okay, the most convenient and the easiest way to find out the inverse of this is by just referring it to a table. So for our purposes, we will be using this. We will not be using the other two methods. Okay, so that's about the Laplace transforms. Okay, have you all understood? Before we move on to the properties of Laplace transforms, have you all understood?
Yes, sir.
Any questions? Okay, if there are no questions, then let's move on to the properties of Laplace transforms. Okay, so there are many interesting properties of Laplace transforms. The first property is called as the Laplace transform of derivatives. So there is a general formula. So suppose I have a Laplace transform. Okay, so let's say I have a function f of t, and let's say the Laplace transform of this function, it exists. And another requirement is this function f of t, it is differentiable. Okay, you can differentiate it at least n number of times. N is a number which I give it to you. Let's say n is 5. Then we are talking about a function f which is differentiable at least 5 times. Okay, then the Laplace transform of the nth derivative. We can find out the Laplace transform of the nth derivative using this formula. Okay, you can see here inside the bracket we have f n t. That means the nth derivative of f. And you are taking the Laplace transform of the nth derivative of f. Okay, what will this be equal to? It will simply be equal to s to the power of n times the Laplace transform of the function itself, then minus, then rest of the terms all will be negative, minus s to the power n minus 1 times the value of the function at t equals 0, minus s to the power n minus 2 times the value of not the function but the first derivative. And you keep going on until you reach the n minus 1th derivative and find out the value of the n minus 1 derivative at 0. Okay, so this is a general formula for finding out the nth derivative of a Laplace transform of the nth derivative. Okay, so just to give you an idea is what's happening. Let's say I put n equals 1. Okay, so for n equals 1, what does this formula become? That means the Laplace transform of the first derivative. Okay, so this is f prime, means the first derivative. It is equal to, just apply the formula, n is equal to 1, so s1. So s1 means simply s. Okay, and L f of t, okay, minus s to the power n minus 1. N minus 1 is 1 minus 1, s to the power 0 is 1. That means we have reached the last term. That itself is the last term. And then the n minus 1 derivative, that means 1 minus 1th derivative. 1 minus 1 derivative is a 0th derivative. That is the function itself. We have to find that 0. So it means only the first term and the last term will exist. And so we'll get 2 terms over here. Is this clear, everyone? Understood? So for n equal to 1, the Laplace transform of the first derivative, that is, we'll have 2 terms. N equal to 2, Laplace transform of the second derivative. Okay, the L f double prime t, what will that be equal to? Again, apply the formula here, s to the power of n. N is 2, so we'll get s square times the Laplace transform of the function, which will be same as before. Then we have minus, then we have s to the power n minus 1, so s to the power 2 minus 1 is s. Then the function, the value of the function at t equal to 0, minus, then n minus 2, so n is 2 here, so 2 minus 2 is 0, s to the power of 0, that means, and then we have f, we have 1 here, that 2 minus 1 is also 1, that means we have reached the last term, so we will have only 3 terms. So this will be the expression for the Laplace transform of the second derivative of a function. Is this clear, everyone? Is this understood?
Yes, sir.
Okay, so let's take an example here. Okay, d square by dt square sine of kt. You already know the answer to this, right? So let's say I want to find out the second derivative of this. So what is d by dt of, first of all, what is d by dt of sine kt? Let's you follow the usual calculus. What is d by dt of sine kt? It will be simply k cos kt, right? And the second derivative, so d square by dt square of sine kt. This is nothing but you'd have to differentiate this again. So this is going to give us, differentiation of cos is going to give us minus k square
Sine kt.
Okay, so this is the answer. This is what we expect. Okay, we expect it to be minus k square sine kt. Now this is usually as per calculus, this is what you expect. Now let's use Laplace transform to arrive at the same result. Okay, this is interesting, right? So we can use the Laplace transform to arrive at the very same result. Let's see how. So here let us say capital F of t, let's say it is equal to sine of kt, because this is the function that I want to differentiate. So this function which I want to differentiate, that I'll call it as the original function f of t. So because in here I'm trying to find out n equal to 2, right? Second derivative, n equal to 2. N equal to 2 means we need the first derivative. We need to know the first derivative. So what is the first derivative? The first derivative is k cos kt. I mean, from calculus we already know the first derivative. So we need to find out the second derivative. So I'll just use the formula. So the Laplace transform of the second derivative. Okay, the Laplace transform of the second derivative is s square L of f of t minus s f0 minus f prime 0. So just substitute everything here. So the Laplace transform of f double prime, which is this one, d square by dt square of sine kt. So you're trying to find out the Laplace transform of this. This is equal to s square, same as before, Laplace transform of f of t. What is f of t? F of t is sine kt. You use substitute sine kt here, minus s into f of 0. F of 0, just put t equal to 0, so sine 0. Okay, then minus f prime 0. F prime is this one, so we have k cos 0. Is that understood, everyone? This step I have just substituted, okay, over here the function and its derivative at t equal to 0. I have just substituted over here, and that's how I got this. Okay, so now we know that sine 0 is 0, right? So sine 0 is 0, so this is going to vanish. Okay, so sine 0 is 0. So here we have s square, the Laplace transform of sine kt. What is the Laplace transform of sine kt? I think just a minute. Yeah, let me put the table of Laplace transforms here so that I can use it. Okay. So coming back here, so I want to find out this one, the Laplace transform of sine kt. So we already know the Laplace transform of sine kt. Where is sine kt? I have given it to you as an exercise. So sine kt is here, and the Laplace transform of sine kt is k by s square plus k square, right? So I just substitute over here. So Laplace transform of sine kt is simply k by s square plus k square. And then here we have a minus k, because cos 0 is 1, so we have minus k. Now you just add this, so we have, of course, there is a s square, so s square k square, so you'll get an s square k square here, and then this s square plus k square you multiply with k, so you'll get s square k minus k cube. So here, of course, this s square k and this plus and minus s square k, that will get cancelled out, And once that is done, then we have this result. The left hand side is just the same. On the right hand side we have this. Okay, so right hand side we have minus k cube by s square plus k square. So now I want to find out this one. Remember what was the original question? Original question is we want to find out the second derivative of this one, right? So to find out the second derivative of this, I want to find out the second derivative, this quantity I want to find out. That means this L, if I bring it to this side, that means I have to take the inverse Laplace transform. Okay, I'm removing L, and that means on the other side I have to put the inverse Laplace transform. So you have to find out the inverse Laplace transform minus k square by s square, k cube by s square plus k square. So I can take out of this one, I can take minus k square, I can take it outside, because k after all it's a constant. So the Laplace transform does not affect the constant, so the constant will come outside. So minus k square comes outside, which leaves behind inside k by s square plus k square. Now let's look for k by s square plus k square over here in this table. What is k by s square plus k square? There it is, right? K by s square plus k square. Can you see that? This is the function, right? So which is the inverse Laplace transform of this one? Sin kt. Is this understood? Have you all understood this? Is this clear, everybody?
Yes, sir.
Okay, so all you need to do is this inverse Laplace, you just replace it with this inverse Laplace that we have here, just replace it with sin kt, and as a result we'll get the second derivative of sin kt is minus k square sin kt, and this is exactly the same result that we got over here, minus k square sin kt. This is what we expected and this is what we got. Understood, everyone? So this is a new way of doing differentiation. Okay, so you all are already used to doing differentiation using calculus like this. This is a new way. There's another use. Okay, there's another usage. You can use trigonometric identities to discover new Laplace transforms. Okay, I'll just show you quickly here what I mean by that. I mean this same problem which we did. Okay, like for instance, I told you, you can find out using you can use the existing results to find out the new Laplace transforms in this table. So you can actually use the same result. So if I want to go it the other way around, so we have d square by dt square sin kt is equal to minus k square sin kt. Now if I take the Laplace transform of both sides, that is d square by dt square sin kt is equal to minus k square, the Laplace transform of sin kt. Okay, so this gives us, we know from this formula. Okay, so from this formula, s square, f of this minus this one, so just substitute here. So this will be equal to s square, the Laplace transform of sin kt minus s f of 0, which is sin 0 minus k cos 0 minus k cos 0 minus k cos 0. This is equal to minus k square L Laplace transform of sin kt. Now of course this will be 0, but from here we get the result that from here we get I can take this onto the other side. So we will get let me bring it here. Let me take this onto the other side. So we'll have s square minus s square plus k square, s square plus k square Laplace transform, s square plus k square times the Laplace transform of sin kt is equal to, because I have taken this on this side, this k I can bring it on the other side, so minus will become plus. So which implies the Laplace transform of sin kt, the Laplace transform of sin kt is k divided by s square plus k square, which is this. The Laplace transform of sin kt is, let me show you, The Laplace transform of sine kt is k divided by a square plus k square, which is basically the same result. So where did we start from? We started from this formula. This was already known to us from calculus and trigonometry. We already know that this is indeed true, and then from here we can find out this. So that means it helps us to find out one more row in this table of transforms. We can find out. So you can build this table of transforms using this idea. Okay, is this clear, everyone?
Yes, sir.
Okay, so the next property is what is called as a change of scale. Okay, change of scale. So given a function f of t with a corresponding Laplace transform. So f of t is my original function, and then f of s is its Laplace transform. Then in this, if I replace, okay, this function f of t, the t if I replace with at, okay, this at, if I replace over here this at, if I replace the t with at, then in this case what will happen? So Laplace transform of f of at, this will be equal to integration from 0 to infinity e to the power minus st f of, because only this inside the function I am replacing t, okay, so f of at. Now we'll do a little bit of manipulation. So over here in the exponent we multiply and divide by s, okay, so we have s by, sorry, multiply and divide by a. So in this here we have s by a, and then we have a into t. You can see here a will get cancelled out, and then we have over here this t I replace with at. So dat, it is nothing but a dt, and then that means I have to divide the entire thing, I have to divide by a, okay, so 1 by a times this one, okay. And then if you look at this one, this is nothing but, this is also a Laplace, this is also a Laplace transform, right? This is the expression for a Laplace transform, okay. So here we are taking a Laplace transform not with respect to s but with respect to s by a. So it's a Laplace transform of s by a. So the Laplace transform of f of at is equal to 1 by a times the Laplace transform of s by a. So this is called as the change of scale, or the scaling property of Laplace transforms. Then we have another property which is called as substitution. I think I'm going to stop here. There are two properties. We have 4 more properties left. I think I'm going to stop here because it is going to be like, it may become a little bit overwhelming for you all. So I'll stop here. Tomorrow I'll do the substitution and then the remaining properties, and then we'll do some applications. And finally, then we'll have the Laplace convolution theorem. Okay. So I'll probably do that tomorrow evening. Is that okay, everyone?
Okay, sir. Okay, sir.
Okay, and I know I have to upload some videos and provide you with the handouts. I'll do that very soon, don't worry, because I have been held up with certain other things these past few days. Wait a minute.